Alright, so I think I'm recording. Let's take a look at problem number 3 of our first day of inverse functions. Alright, so let's take a look at problem number 3. This time they don't give me a finite set, they give me an equation. Well, I'm familiar with this function. With the x having an exponent of 1, this is just the equation of a line, and it's in slope-intercept form. So I know that the slope is 1, that the y-intercept is -6, so I have a y-intercept of -6, a x-intercept of +6. This clearly is a function. It passes the vertical line test. It also passes a horizontal line test, so I expect that the inverse will also be a function. Alright. Our technique for finding the inverse of a function, well, first I would write it in terms of just x and y. I would not use the function notation, at least right now in our work. Then the technique tells us to switch the domain and range, which means that we switch the variables, we switch x and y. So everywhere we see a y, we record an x, and everywhere we see an x, we write a y. Now we'd like to solve this equation for y, so let's add 6 to both sides, and we have that y is equal to x plus 6. I also switched the equality. So now that I have this inverse, and I know that this is a line in slope-intercept form, so the same things, that the slope is 1, that the y-intercept is 6. So I'm familiar with this function. And you could graph it and verify that it's a function because it passes the vertical line test, but we knew that that would happen because the original function, we recognized that this relation was a function, and furthermore that it was a one-to-one function, so we knew the inverse would be a function, and we can use the inverse notation. That -1 is not an exponent, it's just the name of this new function to indicate that there is a relationship to this function, that they are inverses of each other. Alright, so I hope that helps. Let's go ahead and do the next, do 2 problems on this video since that was so short. Now, when I look at this function, I see that it is a parent, I see that the parent function would be the reciprocal function, 1 over x. And the -4 would be a shift to the right 4 units. Then I would take that resulting graph and vertically stretch it by a factor of 3. And then next, go take that result and go up 6. So I have a rough idea then of what this graph would look like. We know in our library of functions that our reciprocal function 1 over x looks like this, with a shift to the right 4 units if this is the line x equals 4, my reciprocal function has just shifted to the right 4 units. Then with a vertical stretch by a factor of 3, now without scaling it, it's hard to sketch that here. Let's use this thing. A vertical stretch by a factor of 3 would stretch the graph away from the x-axis. So up above the x-axis, it's pulling it and stretching it up, and below the x-axis, it's pulling it down. So that's what a vertical stretch would do. And then to lift this whole thing up 6 units after you've stretched it, this thing would be up 6 units. So I can see that not only is the original relation a function that it passes the vertical line test, it also passes a horizontal line test. So I fully expect this inverse to also be a function. Now the technique for finding the equation, let's go through and do that. Let's not use the function notation. Let's go back to x and y. And we know that what the inverse does is it switches the domain and range. So in our solution here, in our technique for finding the equation, we switch the x and y variable. So everywhere we see a y, we write x. Everywhere we see an x, we write y. So let's solve this equation for y. Let's get y by itself. So the term that has the y coordinate, let's start by getting that term by itself. So let's subtract 6 from both sides. And since the right-hand side is a fraction, let's go ahead and make the left-hand side a fraction by placing that over 1. Now, an equation that has a ratio, a fraction equal to a fraction, is referred to as a proportion, or at least that's what we refer to it as. If we now use cross multiplication to solve this equation for y, let's multiply along each diagonal. Along the yellow diagonal, I have this binomial times this binomial, x minus 6 times the quantity y minus 4, and 3 times 1 is just 3. Well, you might be tempted to multiply that binomial, but keep in mind what you're trying to solve. You're trying to solve for y, and on the left-hand side I have 2 factors. So let's get the factor that has the y by itself. Okay? So rather than foiling this out and multiplying it, let's divide both sides by x minus 6. So this is a factor x minus 6. And over here we divide by this factor x minus 6. And x minus 6 divided by x minus 6 is 1. So I'm very close now to having solved for the y variable to get y by itself, because I'm back to 2 terms. And the term that contains my y variable, I want to get that term by itself. Well, that is just y. So I add 4 to each side. So I find it kind of interesting that the original function, the parent function of this original function was 1 over x, and this was just 1, 2, 3 transformations on it. The inverse, its parent function, is also 1 over x, and it has 3 transformations. And we knew when we were thinking about what the original graph looked like that not only did it pass the vertical line test to be a function, but it also passed the horizontal line test. So I know this inverse is also a function. So I can use this inverse function notation, and I can write my final answer like this. Alright, so I hope that helps. Boy, were those numbered right? Huh. Yeah, I was like, I thought I did 3 and 4. Sorry about that. You know, sometimes this, yeah, there's a 2, and then, hey, there's a second number 2. Alright, so I'll do the next, I'll do 5 and 6 in the next video. Hope that helps.